All right, let's do some derivative of the log functions and derivative of an antiderivative of log functions. Okay, so let's see. So like I said, if I were you, I'd pause and see what you get, and then just see if you're getting the same thing I'm getting. So derivative of natural log of x squared. Remember, x squared is it's the input function. So the derivative of the natural log of x squared is 1 over u times u prime. Okay, and notice there's no absolute value bars here because x squared is always positive. Sine is not, so that's why they're including absolute value bars, but that's no big deal for us. We're going to handle it the same way. Is the derivative of the natural log of sine x is 1 over sine x, right? 1 over u times u prime. That's it. And if you're so inclined, that's your cotangent function. All right, this thing looks messy. So this is where our log properties come in. Let me show you your log properties. See if you remember these things. Remember, this one. The derivative of the natural log of a quotient is the difference of those natural logs. That is going to be very helpful. I could do the quotient rule for this one, but look how much easier this problem is if I'm taking the derivative of the natural log of this quotient, if I can just rewrite it first. So it's the natural log of x plus 1 over x minus 1. So that's equal to the derivative of the natural log of x plus 1 minus the natural log of x minus 1. That's algebra. We didn't do calculus there. There's no calculus there. Right? That's just rewriting the log of a quotient as the difference of two logs. And now look how easy this one is. So the derivative of a difference is you take the derivative of each one. So that's 1 over the input function times the derivative of the input function, which is 1. 1 over the input function times the derivative of the input function, which again is just 1 because the derivative of x minus 1 is 1, the derivative of x plus 1 is 1, and then we're done. The other way to do that would be the long way. I don't even want to do it. Right? It would be 1 over u, which is the reciprocal of that. So it would be x plus 1 times x minus 1 times the derivative of u, which is the quotient rule. Dot, 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 dot. I'm not even going to do it, but you should end up with the same thing. Okay, so look out, like always, it's just another example where we want to do some algebra before the calculus if it makes our calculus easier. All right, number 4. X squared plus 1 times, so this is a product rule one. There's no way around it. So the derivative here would be, leave the first one alone, take the derivative of the natural log of x, plus take the derivative of the second one, or take the derivative of that first function, and then leave ln x alone. And then you say, well, what can I do with that? Well, not much. X squared plus 1 times 1 over x is better written like that. And then here I just got 2x times ln x, and that's about the best I can do with number 4. All right. Number 5 is a chain rule. So the natural log of u. So it goes 1 over u, and u just happens, this is one of those tricky ones. U happens to be the natural log of function, times the derivative of that. And that's it. I mean, you could write that as 1 over x ln x, but then you're done with that one. Okay? All right. Let's do some integrals. Okay, so for every single one of these, I'm going to do the same one. I'm going to let u be the denominator. U equals 4x minus 3. Number 1. Du equals u sub, same thing. So u sub process. So dx is du over 4. So when I integrate 1, you could rewrite that. That just looks a little funny, doesn't it? So I would rewrite it as 1 over 4x minus 3 dx, and then do my substitution. 1 over u dx is du over 4. So I pull out the 1/4, and then I integrate 1 over u du, which is 1/4 the natural log of u, which is 4x minus 3 plus c. Now, if you want to check your work, remember, for any integral, take the derivative of that, see what you get. And you should get this. Okay, number 2. So I'll let u equal the denominator. Not even thinking about it, just let it be the denominator. To use the derivative of that. dx is du over 6x squared. And then you'll see how these like work out. If you have that relationship it's close to u prime over u, right? X squared isn't the derivative of 2x cubed plus 1, but it's close. So I'm going to use my substitution. I'm not going to try and manipulate it. Like some people would teach this as try and make this u prime over u. U prime over u. And we could do that by kind of messing with the coefficients. All right, but that to me, that's just like, that's too much work. I'm going to use the u sub method that we already know how to use because we learned it before. All right, and that goes, I called this u, so it's x squared over u, and then dx is this thing, and then you should always get the cancellation you're looking for. In this case, it's, well, in all cases, it should be get rid of my x's. So this helps me with the what constant I need out there. So I got 1 over u du, and then I can integrate, and I get 1/6 times the natural log of u plus c, where u is 2x cubed plus 1. 2x cubed plus 1. Number 3. These ones are tricky because these ones are even harder to see that relationship. Well, maybe not. That one's u prime. So here's what I mean when I do u prime over u. This is directly, if you let u be the tangent of x, then du secant squared. And you could just say, once you know it's u prime over u, you can use your formula. The natural log of u is your answer. So you might like that a little better. I mean, that's pretty quick, right? If it's just u prime over u. But it's not always u prime over u. It's like this one was 1/6 u prime over u. Okay? Or some kind of multiple of u prime over u. So what I would do, I'm going to always do it the same way. I mean, I showed you the shortcut, I guess, or the formula matching just to show you so you're aware of it. But I'd still do number 3 the way I do all of these and let u be the denominator. I let du be the derivative of the denominator. And then I solve for dx by dividing by that derivative. And I do my substitution. So I have secant squared x over u times dx, which is du over secant squared. And now I got my 1 over u, which is, when you integrate it, the natural log of u plus c, which is the natural log of the tangent of x plus c. And yes, it did take me a lot longer to get there, but that method will always work. All right, one more. 0 to pi over 2 sine x over 1 sine x over 1 plus cosine x. So again, plus this way I don't have to think so much. That does look like u prime over u to me, but it's a negative, right? So it's like you'd have to bring in the negative sign, which isn't hard, but again, I don't have to think that much if I just let u be the denominator. It'll work its way out. So u is 1 plus cosine x. Oh, good, we have a definite integral. So we got some more work to do because when I change to u, these bounds change. So u is 1 plus cosine x. So here's how I do these. When u equals 0, sorry, these are x values. When x equals 0, what's u? When x equals 0, u is 1 plus cosine 0, which is 2. Cosine 0 is 1. And then when x equals pi over 2, u is, since u is 1 plus cosine x, it's 1 plus cosine pi over 2, which is cosine pi over 2 is 0, right? So that's just 1. So when I switch this to u, I'm going to switch my bounds. So when x is 0, u is 2. So let's do everything. Du is negative sine x. Dx. Dx is du over negative sine x. So substitute the bounds. When x is 0, use 2. When x is pi over 2, use 1. Sine x, which is going to be gone in a second, over u, because the denominator is u. And this is du negative sine x. So those go away. So I'm done with x. So I got 1 over u, which was my goal. I got a negative. I got 2 to 1. And I got a du. And this is when we get to use that property. If I want to switch the bounds, I'm allowed to do this because this looks weird to me. Anytime I see this, I like to switch them. You don't have to. It'll still work out. But I like to go from 1 to 2 because I like this to be lower than this. It just makes more sense of how we introduce this whole thing. So when I do that, this sign changes, so it becomes positive. So those are equivalent. 2 to 1, negative 1 over u, is equivalent to 1 to 2, positive 1 over u, which I can now evaluate as the natural log of, okay, so it's just, so stay with me here. So it's the natural log of u. I don't have to back substitute from 1 to 2. Okay, I'm done with I don't have to plug in anything to the cosine function because I already did it when I did the substitution over here. Okay, so that means my final answer is plug in 2, plug in 1, and I'm done. ln2 minus ln1. I can drop the absolute value bars because those are both positive. Oh wait, ln1 0. ln2. There's my final answer for that one.